This is a demonstrator video for a heterogeneous distributed software stack developed within the CPSoSAware project. The software stack was developed in work packages 2, 3, and 5. As external pressure encourages centralization and sharing of compute resources, a number of technical challenges become apparent. Applications such as car sensor processing require low latency and high reliability. Efficient utilization of diverse hardware can help reduce the environmental impact of complex systems requiring heavy computation. To address these challenges, in our previously introduced work, we developed an offloading library for OpenCL called PoCL Remote. That work is utilized and extended in this demonstrator. The demonstrated software stack is designed to be portable across a diversity of heterogeneous compute devices, available both locally on the near sensor device as well as remotely on edge compute servers. Switching between local-only and edge server distributed execution is made as seamless, easy, and low overhead as possible. There is basically no difference from the perspective of the main program if the algorithm is executed locally or remotely. To lift the abstraction from the OpenCL-based programming model demonstrated in Work Package 3, we added a proof-of-concept OpenVX layer for describing computer vision domain applications. A heterogeneous task graph is produced from the OpenVX model, which can be cached using the OpenCL command queue buffering mechanism for low latency relaunches, for example to process multiple frames with the same compute pipeline. We also demonstrate Nano-PoCL, an OpenCL runtime tailored for low-end devices, such as a simple RISC-V-based processor in this demonstrator. The final version of the ALMA-IF version 2 is demonstrated with built-in kernel abstraction for launching kernels on FPGA devices from the drone. Flexibility and robustness of the ALMA-IF has been improved from the last demonstrator. It has also been open-sourced as part of PoCL. This is the drone used for the offloading demonstrator. The small-scale Crazyfly nanodrone with the AI deck add-on board contains an SoC which has a RISC-V multicore that acts as a small-scale device that is still capable to offload OpenCL commands through PoCL Remote. The whole application logic is executed on the RISC-V core on the AI deck. The application consists of an OpenVX program implemented in OpenCL. The Nano-PoCL OpenCL implementation pushes the OpenCL commands through the network for remote execution. The laboratory setup for the proof-of-concept demonstrator consists of these three devices: the drone, an FPGA, and a router. The pink Z1 board acts as a compute server with a small FPGA and an ARM CPU that executes the PoCL Remote server. PoCL Remote server uses OpenCL API to forward the commands to a local OpenCL implementation. In this demonstrator, the implementation used is PoCL, which uses the improved ALMA-IF to communicate with the custom FPGA accelerator. The Wi-Fi 6 router provides a high bandwidth and low latency wireless communication link to the drone. The FPGA board is connected to the router with wired Ethernet, through which it receives the offloaded kernel commands. Here the demonstrator is up and running. The proof-of-concept application offloads to the pink FPGA a simple OpenVX program. The program consists of a single min-max-lock node as defined in the OpenVX specification. This node performs a reduction operation to find the pixel with the maximum and minimum brightness values. It also returns the coordinates of the found element. In this application, only the coordinates of the maximum value are used. The drone adjusts its height and orientation to face the brightest spot in the image. The lag in the control reaction stems mainly from the slow transfer of the image. One of the bottlenecks is moving the uncompressed image through the AI deck's slow onboard connections from the RISC-V chip to the Wi-Fi chip. The Wi-Fi connectivity between the drone and the router was also found to be unreliable, which caused additional lag due to retransmissions of network packets. Optimizing the data transfers is found to be the most critical next step for efficient remote offloading. In conclusion, we find the OpenCL API to be a convenient interface for controlling various types of devices in cyber-physical systems. Our PoCL remote extends this API to allow network offloading of OpenCL commands. In this demonstrator, we showed how our tools can be used to expose FPGA accelerators as network-accessible OpenCL compute devices. This allows for even very lightweight devices to perform complex tasks by offloading the heavy parts of the computation. The OpenVX programming model was integrated to improve developer productivity.